Jai Hind everyone. Welcome to another class of microprocessor. In this lecture, basically we will discuss the programming techniques for the microprocessor, that is 8085 programming technique, or we will see some programming example, and in the end we will also see the example for delay generation using the 8085 microprocessor and 8086 microprocessor. So the main contents, as discussed, the main contents of this video lecture will be the programming techniques, or we will see some programming examples for the 8085 and 8086 microprocessor, and in the end we will see a programming example that can be used for generation of delay using the 8085 microprocessor as well as using the 8086 microprocessor. So this is the programming example using 8085. This is a sample program, and this program is using microprocessor 8085. So this is a very simple programming example that can be used for finding the 2's complement of a number. That number is stored in a memory location pointed out at 4200H. So there will be a number that is stored at this memory location 4200, and we have to find out the 2's complement for this number, and the resultant 2's complement is to be stored at this memory location. So the concept is very simple. The given number is available at this location and we have to find its 2's complement, and then 2's complement is to be stored at this location. So the very first step will be, first of all we will take the given number, given hexadecimal number, then in the next step it will be transferred or it will be loaded into the accumulator. So given number will be loaded into the accumulator or the A register. So a given number will be there, and this given number is basically available at 4200. So we have to store this into the accumulator. Then next step will be, the number is now available in the accumulator. So for this given number we have to find out its, first of all we will find out its 1's complement, and after that adding 1 we can get its 2's complement. So basically 2's complement will be calculated into 2 steps. In the first step the given number will be loaded into the accumulator. After that we will find out its 1's complement using the instruction complement accumulator. So complement means basically 1's complement or complement means 1 will be replaced with the 0 and 0 will be replaced with the 1, and for getting 2's complement we have to add 1 immediately into the 1's complement to get the 2's complement. So for adding 1 immediately we can use add immediate instruction. So as clear from these steps, so these basic steps will be used. The given number is to be loaded into the accumulator. So basically we will use the instruction LDA. After that we can find out 1's complement using this complement accumulator instruction. Then we have to calculate 2's complement. That can be simply done by adding 1 immediately into the 1's complement, and then finally we have to store this 2's complement at this location 4300H. So we will use the instruction STA, because the 2's complement or result will be available in the accumulator. Okay, so 2's complement from the accumulator is to be stored at this location. So we will use the instruction STA. So for doing this simple program to convert the given number into the 2's complement form, we will use the instruction first of all LDA to store the given number into the to load the given number into the accumulator. Then ones complement using CMA instruction, then 2's complement by simply adding 1 into that, and the 2's complement now available in the accumulator is to be stored at this location, so we will use STA. So in conclusion, we can see that the 4 instructions will be used. One will be LDA, another will be complement accumulator, then for getting 2's complement we will use add immediately, and then for storing the data available into the accumulator at a particular location we will use STA. So these 4 instructions have been used here. So first of all, LDA 4200H, so this is simply load accumulator. So data available at this location is loaded into the accumulator. Okay, so in this case the given number at 4200H will be loaded into the accumulator. Okay, so the given number for which we have to find 2's complement is loaded into the accumulator. Then simply we will use complement accumulator, that will basically complement the number, or 1 will be replaced by 0 or 0 will be replaced by the 1, or we can say that this instruction will compute the ones complement. Then we have to calculate 2's complement, that is simply done by adding 1 into the ones complement. So we have to add immediately 1, so we will use add immediately 0 1. Immediate data 0 1 is added into the content of accumulator. So this instruction will basically calculate the 2's complement. Then 2's complement result is available in the accumulator, so that is to be transferred at this location. So we will use the instruction store accumulator. So the content of the accumulator are stored at this location. Now to end the program, we can use halt instruction, or simply we can use in the 8085 we can use RST5. After that we can also use the AND. In the end of the program either we can write halt or we can use RST5. So next is delay generation. So in these slides we will discuss basically the concept of delay and how we can generate a particular value of time delay using the microprocessor 8085 or 8086. So we will use the concept of delay using 8085 as well as using 8086. So delay is basically getting some time gap. Delay means getting some time gap, or any event is delayed by some amount of time, so that any task can be delayed by a particular amount of time. So that particular time or time gap is known as the delay. So for calculating the delay, that is most important is what is the frequency of microprocessor or clock frequency that we are using. We will use clock frequency. Let's say there is a microprocessor that is running at a frequency of 2 megahertz. Okay, suppose there is any processor, for example 8085, that is running at a frequency of 2 megahertz. So 1 upon frequency is time. This time period of one cycle is known as the T state. Time corresponding to one cycle or one clock frequency cycle is known as the T state. It is the minimum time that can be used by the microprocessor. So any event that happens in the microprocessor, that will be a multiple of this value T state. For example, if the frequency is 2 megahertz, so time period will be 1 upon 2 megahertz, that is 0.5 microsecond. So time period corresponding to one t state is 0.5 microsecond. So for getting the delay or generating the delay, we will use a set of instructions. Set of instructions will be used, and this set of instructions is repeated again and again a number of times depending upon how much delay that is required to be generated. For example, we can use a set of instructions, and we know that every instruction takes some execution time in terms of t state. For example, an instruction is there that takes 7 t states in the execution. So time period for this instruction will be 7 into t state is 0.5 microsecond. For example, if there is MVI instruction that takes 7 t states, so for executing this instruction we will be requiring 7 into 0.5 microsecond, that is 3.5 microsecond. Okay, so in this way, basically for the given set of instruction or loop that we want to repeat again and again, basically we have to calculate the total number of t states required, and if we know the frequency of the microprocessor, then the time period corresponding to t state is also known. Then we can calculate the total execution time taken, and for particular amount of delay we can calculate how much time the loop needs to be repeated again and again for the required amount of delay. Let's see some examples. Before the example, let's take some general rule for the 8085. We know that in the 8085, in the instruction format, there are only 3 type of instructions: single byte instruction, 2 byte instruction and 3 byte instructions. And single byte instructions usually take 4 t states in execution. 2 byte instructions usually take 7 t states, and 3 byte instructions usually take 10 t states. So for taking the delay loop, we have to consider this while calculating the total number of t states required during the execution of the given set of instructions which are to be executed for computing the required amount of delay. Some more observations are: opcode fetch 4 t states, read cycle and write cycle we require 3 t states for each cycle. Let's see one example. This is a loop, or this is the set of instructions. This is delay loop or set of instructions which needs to be repeated again and again for getting the required amount of delay. So in this case, first of all, we are initiating the move immediately C, that is we are initializing the C register with value FF. That is C register or counter is started so that the loop can be repeated again and again equal to the value that is entered into this count register or counter C. So here this FF means 255 value, 0 to 255. So we are repeating this loop instruction, set of instruction, these 2 instructions again and again up to 255 times. We can see that. So basically for the delay loop concept, as we have seen in the previous slide, basically we have to compute the total number of t states. Total number of t states are required. So as we can see that this move instruction is out of loop. This first instruction is not part of loop. So this will be executed only once. So the number of T states for this first instruction will be only 7 T states. Now these two instructions, DCRC and JNZ loop, these are part of loop. So these are repeated again and again up to 255 times. So for this part of loop we have 40 state, part of loop this we have 10 T state. But we will see that this JNZ loop will require 10 T states only when the condition is not satisfied. When the loop will be terminated, that is in the case of loop termination, in the final cycle when the loop will terminate, instead of this 10 T states, it will take only 7 T states. So in the final cycle, we will take 7 T states, or we can take 10 T states, but we will minus 3. So the total number of T states that we can use here is, in the loop we have 4 plus 10, this is multiplied by 255 times, and when the loop is terminated, instead of 10 it will require only the 7 T states, so we will subtract minus 3 here. Okay, so it will be 255 into 14 and minus 3. So we can see that the total delay will be calculated, or total number of T states will be computed in the loop. As we have seen in the previous slide, the total number of T states will be 7 T states corresponding to the MVI instruction, that is not part of the loop. So we will have 7 T states plus we have 14 T states in the loop repeated by 255 times, and then minus 3 is there. So this is the part of loop, and this is one instruction outside the loop. So total number of T states that we are counting here is, that comes out as, so this part will be 3, 5, 6, 7. So the number of T states in the loop will be 3, 5, 6, 7, and out of loop there is single instruction, so 7 T states are there for this. So 7 plus this one, so that will be 3, 5, 7, 4. So this is the total number of T states required for executing this loop once. Okay, when we are executing that loop up to 255 times FF, when the counter is initialized with value FF, then this is the number of T states. So the delay generated by this loop, amount of delay generated by this delay loop will be 3574 multiplied by the time of 1 T state, and if we have taken 2 megahertz, it was 0.5 microsecond. So the delay generation will be okay. So the delay generation can be computed by dividing this by 2. Okay. So here we can calculate the delay using the 8085. Now the concept of nested loop. Basically, nested loop is required to increase the amount of delay generated. That is, in case of when we require delay of large amount, delay of large value is to be generated, how we can increase the delay? There are some techniques that can be used for increasing the amount of delay that can be generated using the microprocessor. So one of the technique that can be used for increasing the delay is by repeating loop more, and more. So in this case, in the 8085 there is limitation that the register can accommodate only 8-bit value, so it can be only FF. But in the case of 8086, if we have to repeat for the 8-bit, we can use it up to FF. But if we have to generate large amount of delay in the 8086, instead of this CL or CH, we can use a 16-bit counter register, and the loop can be repeated 4 times F times. So one concept is by increasing the value of counter loop, that we can increase the delay. Second technique that can be used for delay generation is by adding additional instruction, in loop. For example, in the previous example, we can use the instruction like this, like move immediately C FF, then we are having DCR C. Then after this we can use an additional instruction in the loop, NOP, no operation, so that execution time taken by the loop in one execution can be increased, and then we can have jump node 0 loop, and that will go to the loop. So as compared to the previous slide, we have added one more additional instruction as a part of delay loop. So during execution of this instruction, we will use additional T states, and these number of T states will be repeated again and again depending upon the value that we are entering into the counter C. So by adding more and more additional instructions as a part of delay loop, we can increase the amount of delay that can be generated. Third technique that can be used for increasing the delay is by using the concept of nested loop. As we know that in the nested loop, multiple loops are executed, one loop inside another loop. So time taken or number of T states will be calculated, firstly for the inner loop, then for the outer loop. So for increasing the time delay, we can use the nested loop concept, that is one loop inside another loop. Okay, so we will see this. This is example of nested delay loop. For generating the large amount of delay value, we will use the concept of nested loop, that is one delay loop inside the another delay loop. So we can see that here is, this is the inner loop, loop 1, this is loop 1. Then we can see that this is loop 2, so we can see that loop 1 is inside the loop 2. So loop 2 is some outer loop and loop 1 is inner loop, and both the loops have been initiated or controlled through the counter value. So this inner loop, loop 1, that is controlled through register C. So register C is initialized with value FF. So inner loop is repeated by this value FF, that is 255 times, whereas this outer loop is basically controlled by this B register. So B register is having value 10H, that is 16 in the decimal. So outer loop is repeated by 16 times and inner loop is repeated by 255 times. So for these two loops we will calculate the total number of T states, and then we will multiply it with the time period corresponding to 1 T state. So as done for the previous example, we will calculate for the inner loop as well as for the outer loop. So here we can see that the total number of T states for both of these two loops will be 57412, and with 0.5 microsecond value of corresponding to 1 T state, the delay generated by this nested loop will be this 28.706 microsecond. As we have seen the loop for the 8085 microprocessor, similarly we can generate the delay for the 8086 microprocessor. Let's see one example. This is one example, delay generation using 8086. This is the similar loop as in the 8085, but instruction used we are having for 8086, like we are initializing the counter with value count, that is to be computed ki how much times we need to repeat the set of instructions for generating the required amount of delay. Then this is the delay loop, and then we will calculate the total number of T states for executing the loop once. So in this case the total number of T states will be 21 and frequency used is 10 megahertz, so it will use 0.1 microsecond. So it will 2.1 microsecond is time required for executing the loop once, and required delays to be generated is 100 millisecond. So how much time we need to repeat the loop, that is computed by this. So this much of times this delay loop needs to be repeated for generating this 100 millisecond of delay. So this will be converted into hexadecimal form, that will comes out to be BA03H. Basically we have to calculate the amount of time required for executing the loop once, and the total delay required is given. So by dividing we can get the for how much time we need to repeat the loop. So this value will be placed in this count value for getting the required amount of delay. So in this way we can generate the delay for the microprocessor based systems using 8085 or 8086. So that's all for this lecture. Thank you everyone. Jai Hind.